Hi, so for today we're going to talk about the family of curves. This is actually a lesson after the elimination of arbitrary constants. And by the way, if you haven't seen my video all about arbitrary constant, it is highly recommended that you first view that video of mine before watching this video. Anyway, our lesson for today is all about the family of curves. What is family of curves? Family of curves are equations that includes arbitrary constants. Okay, so in our last video, we have the topic of elimination of the arbitrary constants, and this equation are mostly standard equation of conic sections, such as of line, the circle, parabola, ellipse, and hyperbola. So basically, what we are dealing with this topic is that, for example, we want to find the family of equations that passing through the origin line. Okay, so in the application of differential equation, we may be able to find the equation of the family of that curves. So for example, for number one here, we have find the differential equation satisfied by the family of parabolas having their vertices at the origin and their foci on y-axis. So in the solution of the family of curves, mostly you are not given by the equation. You are only given by the conditions, and you are expected that you can recall the basic standard equation for line, circle, parabola, ellipse, and hyperbola. Okay, using these conditions, it says the parabolas having their vertices at the origin. So if the vertices are at the origin, it's meaning it doesn't have h and k. Okay, and at the origin and their foci on the y-axis. So, do you agree that in order for us to solve this problem, okay, we have this equation. This condition is actually represented by this equation, wherein we have a foci on the y-axis. Okay, meaning we have this equation y is equals to ax squared, where a actually is any constant. Actually, it's 4a, but we can simplify it into a only. So what we're going to do here is, since this is our equation of that parabola at the vertex having a vertex at the origin and their foci on the y-axis, excuse me. So this is an arbitrary constant. So what are we going to do? Our rule is to count the number of arbitrary constants present in the equation, and if we have encountered already the number of arbitrary constant, then it means it's the same number we're going to differentiate the equation. So in this case, we have one arbitrary constant, so we're going to differentiate this once with respect to x. So this is 2ax, okay? And our main goal is still is to eliminate that arbitrary constant. So we are going to find ways on how are we going to eliminate that. So rearranging the equation, we have a is equals to y prime over 2x. And we're going to substitute it back to our working equation so that it becomes y is equals to y prime over 2x multiplied by x squared. So as you can see, the x here would cancel. We are left with y prime over 2 multiplied by the x, where we have 2y is equals to x y prime, or in other words, we have x y prime minus 2y is equals to 0. This will now be the family of curves that of parabolas having their vertices at the origin and their foci on the y-axis. Or in other words, if you have only 1 degree for the dy over dx, so we can rewrite this equation as we have x dy over dx minus 2y is equals to 0. So we have x dy minus 2y dx is equals to 0. Okay, we can also have this final answer. Okay, so now let's move on at number 2. Find the differential equation of the family of circles having their center on the y-axis. Okay, having their center on the y-axis, as we all know, the standard form for circles is that since they are having their center on the y-axis, this should be x squared, okay, plus y minus, let's say that that origin or that center is actually b, okay, b squared is equals to r squared. So this is a circle, family of circles that has center on their y-axis. Okay. So what are we going to do? Identify how many arbitrary constants are there. Then definitely there is two. We have the b and the r. Okay. Take note that this r squared is actually the radius. So technically it's a constant number. So this means we're going to get the differential or differentiate this equation twice. So let's try that. So we have 2x plus 2y minus b. Okay. Y minus b still y prime because 2. Okay. We bring down the 2 there. Then we copy the whole term here, but minus 1 here. And then, of course, we're going to get the derivative of the inside function, and that is y prime. B is a constant. That is equivalent to 0. So that we have 2x plus 2y minus 2y prime, I mean, and then minus 2b y prime is equals to 0. Okay. So, rearranging the equation. Okay. Rearranging the equation. And by the way, we can actually cancel out the 2's here. We have canceled the 2's by multiplying it, the whole equation by 1/2. So we have x plus y prime minus by prime is equals to 0. So we have eliminated the first arbitrary constant. And now it's time for us to again eliminate this constant. So what will we do? X plus y prime is equals to by prime. And if we're going to divide or multiply this whole equation by y prime, what are we going to get? We'll be getting b is equals to x plus y prime over dy prime. And if we're going to differentiate this once again, we're going to eliminate this b here. So 0, because that is a constant, and this is what do you call this? The low, the high minus high, the low rule. Okay. So for this differential equation or this equation, so what are we going to do? Low, the high, low. Okay. Derivative of high is 1 plus this is a product rule. Might as well copy this and find the differential, the derivative of this, that in this case that is y double prime, plus copy the second one and get the derivative of this, that is y prime, okay, minus the low, the high minus high, copy the numerator, and then you're going to multiply it by the by the derivative of this. So we have y, okay, double prime, okay, over y prime squared. Of course, that's the formula for the for our derivatives. Okay, so we're going to simplify this. So we have 0, we have y prime plus y prime y double prime plus, of course, this is y prime squared. So we have y prime cube. Okay, y prime times y prime is y prime squared multiplied by another y prime, that's y prime raised to 3 or cube. So of course, minus x y double prime minus y prime y double prime. I'm only distributing the negative sign and the y double prime here, so that as you can see, this would cancel. Okay, this would cancel out. And oh, of course, over y prime squared. Okay, this would cancel out. So we are left with 0 y prime plus y prime raised to 3 okay, minus xy double prime divided by y prime squared. So simplifying this, we have to simplify this differential equation. By the way, what I have performed here is the quotient rule. I forgot earlier. That is the quotient rule for derivative. So we arrive at this answer. So normally, the differential equation does not have any denominators in it. So might as well, we can cross multiply this. If we're going to cross multiply that, we are left with 0 is equals to y prime plus y prime cube minus xy double prime. And if we're going to get the multiply this by negative 1, we have x y double prime minus y prime, okay, of cube minus y prime is equals to 0. Hence, this is the family of curves of the circle, okay, with center on the x-axis, if I'm not mistaken, or center on the y-axis. Okay, so that is our differential equation. For number 3, find the family of curves of straight lines with slope and y-intercept equal. Okay, so y-intercept and slope are equal. So for our solution for that, we have this equation of circle y is equals to mx plus b. We have the slope intercept form, but it says that the slope is equal to the y-intercept. So we can replace this by y mx, okay, plus m, okay, because the slope is equal to the y-intercept. Might as well replace that by m, okay, and we get the derivative. So by the way, how many arbitrary constants do we have here? Okay, it's actually replaced by m. So simply we can get y prime that is equivalent to simply m, because this is a constant. This would be 0. This is the mx. So differentiating it with respect to x will leave us y prime is equals to m. So in order for us to eliminate this, we are going to substitute that, or my mistake, in this equation. So we have y is equals to okay, so we have y is equals to uh, y prime, okay, y prime x plus y prime, okay. So simply we substitute this into this. So we have the differential equation y is equals to, factoring out y prime, we have x plus 1, okay, and we have x plus 1 y prime minus y is equals to 0. Or this can be the answer, or we can actually distribute the dy and dx of the y prime. So what will happen here is that we have x plus 1, okay, multiplied by dy over dx minus y is equals to 0. As you can see here, x plus 1, we have dy minus y dx. Okay, this can be also our answer. Okay, that's for number 3. So for number 4, circles with center at the origin. Okay, circle center at the origin. So we have the standard form of circle equation for circle as this, as one circle that having a center at the origin, x squared plus y squared. So how many arbitrary constant? This is a constant, okay? So we're going to differentiate this once. So we have 2x plus 2y, y prime, okay, is equals to technically 0, because this r squared, what I said, is the arbitrary constant. It can be any number. That's the radius. So the derivative of the constant is actually 0. So what are we going to do here? So we can multiply this both by 1/2, simplifying. So we have x plus y prime is equals to 0. This can be our dE. Or we can have this x plus y, okay, dy over dx is equals to 0. So we have x dx plus y dy is equals to 0. So this is now the differential equation. This form can be also the answer, and this form can be also the answer. Okay? So if we have y prime, might as well we can distribute the dy and dx in order for our differential equation to look neat, okay, as possible. Okay, so for number 5, we have the circles with center on the x-axis. So the solution, first, we need to have an equation of circles with center on the x-axis. That is x minus h, where h is the coordinate of the center of the circle, plus y squared is equals to r squared. So we have two arbitrary constants. We have this coordinate h, and we have the radius r. So technically, we're going to differentiate this twice. So we have to differentiate this 2x minus h. Okay, differentiate the inside function, that's with respect to x, that's 1, plus 2y, y prime is equals to 0. So in other words, we have 2 times x minus h plus 2y, y prime is equals to 0. Then we're going to multiply both sides of the equation by 1/2 so that the 2's will cancel here. So we have x minus h plus y, y prime is equals to 0, or x minus h plus y, y prime is equals to 0. So isolating again the arbitrary constant. So we have x plus y, y prime is equals to h. Then differentiate again. Okay, differentiate. This is the second time we're going to perform the differentiation here. So we have the derivative of x is 1, plus this is a product rule. Okay, copy the first, then multiply it by the derivative of second. So y double prime, plus, of course, copy the second one, we have the y prime, and get the derivative of the first, we have y prime also. That is equivalent to equal to 0, because the derivative of this constant is 0. So simplifying, we have 1 plus y double prime plus y prime squared is equals to 0. And here is our differential equation. So in other words, if we're going to rearrange this, okay, it's still the same, okay? Still the same. So we have the answer with the circles with center on the x-axis. Okay, that's differential equation. Right, so let's proceed with number 6. Straight lines with slope and x-intercept equal. And again, for our solution, we shall be using the, we have this y is equals to mx plus b. We have the slope-intercept 4, but it says that the x-intercept and the slope are equal. So if the x-intercept, we want to get the x-intercept here, we let y is equals to 0. Okay? Mx plus b. Okay, and we're going to get x, of course. X here would become equal to negative b over m, of course. But it says, according to the condition, that the x-intercept is equal to the slope. So, we're going to substitute x is equals to m. Might as well we have m is equals to negative b over m, so that we have b is equals to the negative of m squared. Okay? So far we have not yet performed differentiating. Okay? Differentiating or the derivative. So, since these two are equal, this is a constant equal to another constant. So, we only have one arbitrary constant. So, this b is equals to negative m squared. We can substitute here on our working equation labeled as number 1. So, therefore, if we substitute that, letter b, we have y is equals to mx minus m squared, because b is equals to negative m squared. Okay, so if we're going to get the derivative of this, first derivative, so we have m plus 0. Okay, this is a constant, so when derived, when differentiated, it should be equal to 0. And this is a with respect to x and some certain constants. So y, if you're going to get the derivative of this, it should be equal to m. So we have y prime is equals to m. Okay, and this m, we're going to substitute with the working equation here above. again. In order for us to eliminate this arbitrary constant, so we have y is equals to m is y prime x, okay, minus y prime squared. Okay. So what will happen here is that this is our differential equation. So I'm just gonna do a little variation in this. So it can be rewritten as y prime squared minus x y prime plus y is equals to 0. So this would now be the differential equation for this condition number 6. Straight lines with slope and x-intercept equal. So what we did is first we get here we let y is equal to 0 because we want to know the x-intercept, and then we get the x in terms of this equation. We have negative b over m, but according to our condition, the x-intercept is equal to the slope. So we substitute x with m, and then we get the in terms of b, so that we can substitute it back to the original equation. So because we want to eliminate the arbitrary constants here, so we have negative m squared. So this is our working equation, then get the derivative, and then back substitute it again to the original equation to eliminate this arbitrary constant, and hence we have this differential equation. Okay? So for our next example, we have find the family of parabolas with vertex on the x-axis and axis parallel to the y-axis. So vertex is on the x-axis and an axis parallel to the y-axis. So it means it's either opening upward and downward. So it has a vertex on the x-axis. So it means we have the equation x minus h squared equal to 4ay. This should be our working equation. It has a vertex in the x-axis and it's opening either either upward or downward, and it has an axis parallel to the y-axis. So if we're going to solve this, okay, as we can see, we have two arbitrary constants. We have h and a here, okay, but this 4a is a constant, okay. Remember, that's the latus rectum, okay. That is a constant, okay. So we can actually replace 4a with simply a, because 4a, 4 times a constant, would always be a constant. So might as well replace that simply by a, okay, because it's still a constant. 4a is still a constant, is equal to a, okay. So our concern here is that we have two arbitrary constants, which is h and a. So we're going to find the derivative twice. Perform the derivative twice. So let's start. We have 2x minus h, okay, equal to, this is differentiating with respect to y. So we can actually factor out this constant and get the derivative of this. That is still a y prime. Okay, as you can see here, after differentiating, none of the arbitrary constants were cancelled. That is because we'll be using another technique in order for us to eliminate the arbitrary constant by simply substituting. So we have, if we're going to simplify this, this should be our first equation. That is our first derivative. So let's simplify. 2x minus 2h is equals to a y prime. And if we're going to get the second derivative here, okay, what will happen is that this is a constant, so this would be eliminated. So finally, so we have 2 with respect to x, that is still 2, and this is still a y double prime. So this is our second derivative. Luckily, we actually got rid of the h, which is one arbitrary constant. So our goal is to eliminate again the a. So from here we have a is equals to 2 over y double prime. So, and what are we going to do with this? We're going to substitute this into the what? Into the first derivative equation. Okay? So that we can eliminate the what? The excuse me, the a. So what will happen here is that continuing here, so we have 2 times x minus h is equals to 2 over y double prime multiplied by y prime. So as you can see here, these 2's will cancel. Okay, so we have x minus h is equals to y prime over y double prime. So we can isolate still the h. There is still the h. Okay. So what will happen here is x minus y prime over y double prime is equal now to h. Okay. This is our expression or equation 4 for substituting this a into the first derivative. But what are we going to do with this is that we haven't yet substituted any values to our what working equation. So what are we going to do is that we're going to substitute this into our working equation together with the a here. Okay, in order for us to eliminate the arbitrary constant. Okay, so we differentiated twice. Okay, so we're going now to substitute this value of a again and this value of h into this working equation in order for us to get the what? The family of curves. So we have x minus h. Let me just rewrite first our working equation is equals to a y. So what will happen here upon substituting h? So we have x minus y prime over y double prime. This is raised to square is equals to a, that is 2 y double prime multiplied by simply y. And again, we're going to simplify this. So, it is much easier if I'm going to distribute the negative sign here. So what will happen in here is x plus negative x plus y prime, y double prime squared equals to 2 over y double prime times y. So let's expand this whole term. So we have let me just redraw this and redraw it into a bracket instead of parentheses. So first, to expand this, we have x squared, expand the first. And then the second term would be, we know that the result of this is 3 terms, okay? So what are we going to do with this one is for the second term we have what? Let's say plus, okay? X multiplied by this second term, okay? And multiplied by 2, of course. Okay, plus, of course, we're going to what? Square this, okay? Square this. So perform square with that, we have what? The negative x squared, that should become x squared, okay? So, and then multiply all of this. That should be negative 2x y prime over y double prime. Okay, what are we performing now is the square of this because that's the shortcut. Okay, so that we would not be able to use FOIL. That's the shortcut. You square this first, and for the second term, you multiply all of this. Multiply. Okay, we did that here. And of course, for the last term, you're going to square it. So I'm squaring it. Negative x squared. So we have x squared. Then the second term is multiply again all of this. And then what will happen to the last one? So to the last one, we're going to get the square of that. So that is y prime over y double prime squared. Okay? That's the expansion. And we are now left with 2y over y double prime here. So as you can see, upon simplifying this, so what will happen is that we have x squared minus what? We have minus 2x squared because 2 times x is 2x. Distribute the 2x, negative 2x squared. And then we have plus 2x y prime over y double prime plus x squared minus 2xy prime over y double prime plus the y prime over y double prime squared is equals to 2y y double prime. Upon simplifying, we know that x squared plus x squared is 2x squared minus 2x squared. So this should be cancelled. Okay? Plus 2xy prime over y double prime is cancelled by this term. Okay? Because it's minus. And you are left with what? This equation. Y prime over y double prime squared is equals to 2y y double prime. So, upon simplifying further, we have y prime squared over y double prime squared is equals to 2y y double prime. So, we can cancel out this. Okay, what will happen is that we have y prime of squared over y double prime is equals to, we have 2y. So in other words, simplifying this will give us the differential equation for this family of curves. So we have 2y y double prime, okay, 2y y double prime minus y prime squared is equals to 0. And this should be the differential equation of the family of curves given by or asked by our problem. Okay? So it's a lengthy process as you know, but definitely our goal is to eliminate the arbitrary constant. First, determine how many arbitrary constants. We have 2. Then we differentiate it. So what happens? We obtain a value of a and substitute it back the first derivative. So that we can get the other arbitrary constant. And after that, we're going to substitute this h and a to the working equation, which is the original equation, which is this. And then, what? Then solve it, okay? Simplify it. Then, again, you arrive at the correct answer. Okay, let's continue. Okay. For number 8, find the family of curves or differential equation with parabolas with vertex and focus on the x-axis. So we have the focus on the x-axis and vertex on the x-axis. So definitely it's a equation having this standard formula again for what? For parabolas with vertex and focus on the x-axis. This would be our working equation. Y squared is equals to 4ax minus h. Okay, vertex here at the x-axis and the same. The focus is the x-axis. Okay, so what are we going to do? Again, this 4a is a constant. So 4a is a constant. We can simply write 4a as simply a. Okay, so we have y squared is equals to a x minus h. So in this equation, we have two arbitrary constants. We have a and h. So definitely, we're going to differentiate this twice. So let's differentiate. So we have 2y y prime. Okay, and that is equal to, well, of course, first, before we differentiate, to avoid error, we should what? Distribute this. Okay, so if we're going to differentiate this, ax, ah, this is simply 0 because this is constant. So with respect to x, this will be simply a. Okay, and in order for us to eliminate a, okay, we take again the second derivative in order for us to eliminate that constant because we have already eliminated the h here. So if we get the derivative, we have 2 product rule y double prime plus y prime multiplied by the derivative of this is simply y prime also is equals to 0. The derivative of the constant a is 0. So simplifying, we have 2y y double prime plus 2y prime, of course, squared is equals to 0. And we can simplify this differential equation by cancelling out 2 so that we have the differential equation y times y double prime plus y prime squared is equals to 0. So this should be our differential equation for this problem. Okay, down to our last example. Find the differential equation family of curves of the ellipse with center at the origin. Now, the standard equation or solution for ellipse is that it is x squared over a squared plus y squared over b squared is equals to 1. Okay? So, where a and b is actually constants, right? So, what are we going to do here is we have two arbitrary constants. We're going to derivative or differentiate this equation twice. So, rearranging the equation first, we have x squared times b squared plus a squared times y squared is equals to a squared b squared. Okay? So, if we're going to get the derivative of that, first derivative, with respect to our, of course, to our x and y, so we have 2x b squared plus 2a squared y prime. Okay? With respect to y, we have 2y, copy the constant, and we have the dy over dx, which is the y prime. That should be equal to 0 because these two are constants. So we can simplify this by simply eliminating the 2. We have x b squared plus a squared y prime is equals to 0. Now, this is our first derivative. Okay? First derivative. Well, of course, since we have two arbitrary constant, we need to differentiate it again. So again, differentiating this with respect to x. Oops, I'm so sorry. With respect to x, so we have simply b squared plus a squared. Now, this is the product rule again. Y double prime plus y prime times the derivative of y is again y prime, and that is equivalent to 0. So, upon simplifying, we have b squared plus a squared y double prime plus a squared y prime squared is equals to 0. Okay, so this is a type again of a problem wherein even if we differentiate this equation twice, still the presence of the arbitrary constant is still there. So might as well we find a way on how we are going to actually eliminate the constants by actually substituting it to the either to the first derivative or to the original working equation. Okay, so what are we going to do? First is we isolate b because we can isolate that. We have b squared minus a squared y double prime minus a squared y prime squared. Okay? And we can substitute this b squared actually into the first derivative that we've got a while ago. Here, this equation. Okay, this equation. Okay? So we can substitute it that there. So what will happen here is that upon substituting here, okay, upon substituting there, so b squared would be x multiplied by the b squared negative a squared y double prime minus a squared y prime squared. Okay, that's the b squared plus a squared y prime. Y prime is equals to 0. Okay? So, let's try. Distribute a squared x y double prime minus a squared x y prime squared plus a squared y prime is equals to 0. As you can see, the b, which is the arbitrary constant b, is now cancelled. So, we are only left with a. And to eliminate a, okay, we have to do some algebra here. Okay? So in this case, we can factor out what? The negative, okay, negative a squared x, both from these terms. So that we have y double prime minus y prime squared, okay, plus a squared y prime is equals to 0, of course. Okay? So, if we multiply this equation by 1 over a squared, then definitely this a squared would be cancelled. Correct? That's correct. So, we have now the negative x, y double prime minus y prime squared plus y prime is equals to 0. Viola, we have eliminated the arbitrary constant. So, we have to simplify. That's the final step. Okay? Plus y prime is equals to 0. And we can multiply this by negative 1. Okay? So, what will happen? We have the answer x, y double prime minus x, y prime squared minus y prime is equals to 0. So, this is our differential equation of the families of the curves of an ellipse with the center at the origin. So, if you like this video, if you found this video helpful, thank you so much for listening. This is Engineer Abat. Please subscribe to my channel. Thank you. God bless.